Thanks for everyone for being here. Today I'm going to present a topic on motion planning optimization. So the talk I'm going to be giving is based off a previous JuliaCon in 2020 on conic optimization in Julia and JuMP. So this is an alternative approach to motion planning using optimization-based methods. So some of the challenges with existing methods you may know include grid-based methods. These don't necessarily produce smooth trajectories or optimal trajectories. Sampling-based methods are typically computationally expensive. And here is another approach that may be promising to these issues. So using MICP techniques or mixed integer conic programming techniques is what we're going to show here. So just a brief recap of what an optimization problem is. So there's several things that define it. One is an objective function or a cost function. And that's a function that we want to minimize or maximize. So think of the smoothness of a trajectory or the cost associated with executing that trajectory. Then we define a set of constraints. So using equalities or inequalities. And these sets of constraints must be satisfied. And if any one constraint isn't satisfied, then the problem is immediately infeasible. So some good functions for optimization problems in general are convex or affine, and the reason for this is that it is easy to solve such problems. One of the things that convex problem functions give you is that if you any optima that you find that is local will also be global. So think of a bowl shape type function. So if you start from any part of that function and go downwards to the minimum point, you will always find that point. And probably something to take away from this is that optimization is typically hard because some of the challenges is just trying to pose the right problem to solve. Sometimes we want to solve for many things, but it's impossible to solve for everything. Sometimes the constraints are too tight, and we just got to relax those constraints a bit. And it's sort of an art in itself because we're always trying to find better ways of optimizing the problem. And that could involve better solvers or basically reformulating the problem. So here's a picture of what trajectory optimization might look like. So in 2D, you can see some black dots here. So that is a trajectory, and the colored spaces are basically regions in space that an object like a car or a plane or whatever it is can go through. Areas that are outside those regions are you can call obstacles. What we're going to do is we're going to represent this obstacle using polynomials, and the mixed integer aspect of it is we're going to define these multiple different safe regions. So it's a bit hard to see here, but you can basically see one safe region and overlapping with another. And yeah, that's basically it. So one of the other things that this picture shows you is there's a blue one and a green one. And that is just showing that if your safe regions are not generous enough, you may not be able to necessarily find a feasible trajectory. So one way of doing that is just to increase or decrease the sizes necessary. In 3D, the extension of this optimization problem is pretty trivial. Using Makie.jl, I've rendered some graphs, and the yellow boxes here are basically the safe regions, and you can faintly see a trajectory sort of going around the safe region from some starting position to an end position. If you look closely enough, you should be able to see that it never gets outside the colored regions, and that's exactly what we want to show. This other one visualization at the bottom here is just basically showing the obstacles in a different color. The output you would see when you're solving an optimization problem might look like something like this, and this console output would tell you how the optimizer is solving that problem. So it'll give you statistics like how many iterations, how long it's spending in each iteration, so on and so forth, and that would tell you how you might want to measure the performance of this formulation, this problem. So you can see that here's another way of visualizing a trajectory. So a trajectory is made up of different segments. So you can see one segment here, and the start of another segment here, and then finally a third segment here. And you can see that each segment is allocated to a particular region in space. Some of the shadings are darker than others, and that's just to illustrate that these regions overlap. So the mixed integer aspect of this problem is basically given a number of segments, how would you allocate those segments to different safe regions? And once you've got that allocation right, then you get the trajectory from your start position to end position. So other than that, you just let the optimizer run, and it should come up with the solution automatically. So here are some preliminary results that I've got. So this was using a package called, a few packages, Pareto, Hypatia, and MOSEK. So Pareto, Hypatia are Julia packages, and they're to solve the conic part of the optimization problem. The package MOSEK is to solve the, using the outer approximation algorithm, the mixed integer part of the problem. You can see here that as you vary the number of trajectory segments, the blue line, so we got two different trajectories from two different start and end positions, and you can see the what that looks like with 4 segments, 5 segments, and so forth. You can see that in general, the solve time increases as you add more segments, but that isn't necessarily the case here for 6 segments with this trajectory one. So sometimes it ends up being faster with more or less segments. Okay, so another solver that you could use is the high solver. This is one that I've tried, but wasn't able to get reliable results. So for anyone that can extend this work, it'll be great to make it work with highs, because it's basically an open source solver. Okay, so other things that one may want to try is warm start. So if we're looking to make this go a bit faster, you might want to, if you've solved the problem once, then you can solve a similar problem with a slightly different initial position and start position. What we see in the results here is that without a warm start, we don't do particularly well, and with a warm start, we save a bit of time. So as long as the problem is as quite similar to the previous problem that you already solved, then you may see some performance benefits. in terms of compute time. So other things, if you're using JuMP and specific to the solver that you're using, you can also optimize with different parameters as well. So here I'm taking the highest optimizer and specifying the model with its with the solvers that I'm using, and you can see the parameters that I'm using for this outer approximation solver. So these parameters, so it's basically a primordial solver here, and I'm basically fiddling with the number of iterations, the feasibility constraint tolerances, and basically trying to see how I can make this go faster. And obviously, you may not want to do this, but this just illustrates how you interact with that particular optimizer. We get some sort of interesting results. You can see that if we prematurely stop the optimizer, it wouldn't give as good of a solution. And you can see some of these points here are sort of closer than they need to be to each other. So we pay a price for making that trade-off. And so I just basically the take-home message is we just need solvers that we can control how they optimize the problem. So so this output here shows what we want to see. We can see that we want these numbers to be as close to 0 as possible and meet the infeasibility constraints. Obviously, we want number of iterations to be as low as possible. And most importantly, we want to see that it's arrived at an optimal solution. So from this output, you can collate the results and then graph it to show how that changes over time. One of the things when you're using mixed integer techniques, so here I'm using what's called a big M method, and this big M method is a set of constraints that you add to determine how you assign the trajectories to each other. So a good rule of thumb around picking those numbers is just to select the edges of the map of the set of obstacles that you're in. So the way it's implemented, so basically this is what the code looks like. We're minimizing the trajectory jerk, which is the derivative of the acceleration in time. So what that is basically the smoothness of the trajectory using polynomials. And in this instance, we are using box constraints. Here we set the initial conditions, so we're setting the initial position and the final position. We're also setting the initial velocity, final velocity, and acceleration. Over here are the box constraints, and this is using this big M notation. This part here, SOS, stands for sum of squares. So we take a polynomial, we square it, and what that gives us is a polynomial space, and that is a convex cone. So it's not. So basically, we need to do that in order to make the problem convex. This ZIR is basically making sure that we enforce the mutual exclusiveness of assigning trajectories to safe regions. And that's basically can take only values 0 or 1, and that is the n by r data structure. Okay, so these are the constraints here, are the stitching conditions. So basically, to create a trajectory from segments, we have to stitch the end of one trajectory to the start of the next trajectory. And so we do this for the position, the velocity, the acceleration in 3D space, so for x, y, and z. So that works for box constraints, but we don't just want to represent safe regions as just boxes. So for arbitrary shapes, we can approximate that using polyhedrals. So to create a polyhedral, all we do is just define a set of half spaces, and those half spaces are basically in this form. So ax less than or equal to b or greater or equal to b defines a half space. So equality gives you the hyperplane, and then the half space is basically everything above or below that hyperplane. So another way to sort of show that as a set of equations is here, and this shows also the use of the big M notation. The only thing that changes here, if you're using half spaces instead of box constraints, what you can do to represent this is to define the data structure half space. You got a set of coefficients x, y, and z, and c, and the inequality to represent the direction of that space. And so by varying x, y, and z, you get different shapes. So the half space is sort of going off in different directions. And when you put that together, then you get a polyhedron. Okay, so some further work. We need to extend to include, well, this has already been done. Want to make this go faster. This is actually pretty slow, so I'll do a demo of what this looks like. But obviously, you want to take advantage of parallelism, and so there's work that's going on to come up with other solvers that use CUDA, for example. So this is a paper from University of Chicago, looking at primal dual methods for GPUs. Other things that I want to look at is possible reformulations of this problem, extending it to solve for jounce, for example, or the fourth derivative of position. So that doesn't currently work at the moment with MOSEK. Extending it to different solvers. So maybe not everybody has a MOSEK license. They might want to use a different solver, and that's fine too. One of the good things about this little project is basically everything is synthetically generated. So the maps and everything you don't need necessarily real world data, but although that may be nice, but that isn't necessary to gauge performance, because you can always add obstacles or trajectory segments and make the model as complex as it needs to be to measure the performance. Other things is just looking at different optimizers and what can be done with them, because what can be done to make things go faster. And to resolve some numerical instability issues. So one of the things that I ran into challenges with is just things blowing up in size when you look at the matrix, for example, and that results in infeasibility issues. So just to wrap up, I'll go and show a demonstration. And we might need to wait a bit, but it shouldn't take that long, actually. So I've posted on GitHub this Pluto notebook, and what that gives you is basically what we've gone through, and you can play with this yourself by trying different optimizers and changing the constraints, playing with boxes, and just getting a feel for what this problem is about. And I think this is an interesting problem because you're going to see it in motion planning for robotics, for autonomous vehicles, for UAVs. They're all trying to solve the problem of getting from point A to point B and finding the best possible trajectory. The other thing that I like about using the optimization approach is because you're just able to embed a lot of these different constraints in just in this sort of way. But one of the things that I probably see that may be an issue with this is it's probably not suitable for real-time applications yet because you need to throw in a MOSEK solver into an embedded system, and I don't think that's going to happen soon. So let me know if you find issues. Just raise the issue on GitHub if you do. And you've got the usual communication channels like discourse or email. And I'll look into any issues you may find with the use of this implementation. So it's almost done. You can see it didn't take a long time to pre-compile. So any questions? So this is using polyhedral constraints. So I've commented out a few lines here. You can see if you define half spaces to represent box constraints, you would need a lot of to define a lot of half spaces for the different polyhedrals. But obviously you can generate that, so that's a non-issue. So I'll just show how easy it is to use box constraints instead. So I'll just comment, uncomment out several different lines. And if we let this run again, you'll see the trajectory. So that's what it looks like with wireframes. Okay, so that's all for the talk. Thanks.